Okay, so in this video, I will be assuming a little bit of outside knowledge, which you'll see in a bit. So if you don't follow along with everything in this video, that's fine. It's not central to the story. It's more of an aside. So you can safely move on to the other videos without really losing much. But in this video, we're going to explore a bit more about how to find these special vector fields that we have been talking about in the last few videos. And so as a reminder, in the last video, we found these two vector fields, f and g. F was defined on everywhere on R3 minus the z-axis and defined as follows, and had the property that the curl was 0 everywhere it was defined, but it was not the gradient of any function. And G, similarly, was defined as follows. It was defined everywhere on R3 minus the origin, and it has the property that the divergence is equal to 0, but it is not the curl of any vector field G prime. So I claim that the existence of these vector fields tell us something about the topology of our space, similar to how we had in 2 dimensions. Specifically, that something which has 0 divergence but is not the curl sort of corresponds to a 0-dimensional hole, like missing the origin. And something which has 0 curl but is not the gradient of any function corresponds to a sort of 1-dimensional hole, like the z-axis in our space. Now, if you remember in 2 dimensions, what we were looking at was functions which had 0 curl but weren't the gradient of any other function. And if we had n holes in our space, then we could take our special vector field at the origin and sort of translate them to those n different points. And we had n independent vector fields which had 0 curl but weren't the gradient of any function. And the fact that there were n of those functions told us that there were sort of n holes in our space. We can do a similar thing if we have like a couple of points missing from our space. So for example, if we had a couple of points missing from R3, then we can translate G to those different points. And each of those functions will have the property that the divergence is 0, but it won't be the curl of any other function. And they'll sort of satisfy independent criteria of like, if you integrate over a certain sphere surrounding exactly one of those points, but none of the others, then that will be non-zero for one vector field, but 0 for the rest of them. And that'll give you sort of n functions, which will tell you in a sense that there are n holes in your space. But it's not quite clear how to do that with different one-dimensional holes in this case. So for example, if I give you the space, which is like R3 minus this unit circle S1, so S1 is going to be parameterized by gamma, which is going to look like cosine t sine t 0. So this is the unit circle in the xy plane. And if we were to look at R3 minus S1, then I'm claiming that there should be some vector field defined on this space, which will have 0 curl everywhere where it's defined, but it will not be the gradient of any function. So the question then becomes, how can we find such a vector field? And it turns out that there is actually a very nice way of explicitly computing such a vector field. And the only unfortunate truth about this is that the physicists beat the mathematicians to figuring this out. So if you've taken some electromagnetism before, then you might actually recognize f and g as being some very special vector fields. So if we were to look at what the magnitude of f is, then at any point x, y, z, the magnitude of f is going to be 1 over root x squared plus y squared. So in other words, it falls off as like 1 divided by the distance from the z-axis. And sort of rotates about this positively oriented z-axis. So it's pretty much the vector field, which is the magnetic field caused by if there were a current going upwards in the z-axis. And similarly, G is a vector field that points radially outwards, and it falls off as 1 over r squared. So it's sort of like the electric field that's caused if there was a point charge at the origin. So what that suggests is for this problem, we can sort of look at, okay, what would be a magnetic field if we were to pretend that there was a current passing through our loop, which we're excluding from our space or our one-dimensional hole. And over here, we can look at things which are electric fields if there was some charges placed at our holes in our space. And so I claim that the magnetic field and electric field satisfy these properties, that the curl is equal to 0, but it's not a gradient for a magnetic field, and the divergence is 0, but it's not the curl for a electric field. So first, let's discuss the magnetic fields in detail, because this one we sort of have a grasp of how to deal with multiple holes. We can just translate G, but this one it's sort of a bit harder to get a grasp on. So what we can do is we can pretend that there is some current I, some constant current that's flowing through this loop S1. And we can try and see, okay, what is the magnetic field at some random point um, away from the loop S1, which is generated by this current? So what we're doing is we're going to try to compute this magnetic field explicitly, and then it turns out that Maxwell's equations will show us that this magnetic field has these exact properties. So how does that work? Well, Maxwell's equations tell us in like regions with no current, we're going to have the following, that the curl of B is equal to 0. And that's pretty much Ampere's law. And this tells us that if we compute this magnetic field generated by this current I, then the regions with no current are going to be precisely every single point in R3, which is away from this unit circle S1, because S1 is where all the current is in our space. So what this means is that this magnetic field will have 0 curl everywhere it's defined, which satisfies our first property. So now how can we show that it's not the gradient of any potential function? And for this, we can use the integral form of Ampere's law. And what that tells us is that if we have some loop C in our space, and we integrate B along this closed loop, then we're going to end up with mu naught times the current which is enclosed inside the loop. So in this case, there's no current going through the loop, so the integral around this loop is going to be equal to 0. However, if we were to analyze this loop, which sort of links together with our unit circle like so, then we're going to have that there's some current passing through this region of the loop. So if we call this loop C, then the integral over C of B dot dl is not going to be equal to 0, because we're assuming that there's some current passing through our loop our whole S1 here. So remember that the condition that the line integral of our vector field is non-zero over some closed loop C was exactly what we used to show that our magnetic field or any vector field cannot be expressed as the gradient of some potential function. And so pretty much this differential and integral form of Ampere's law from Maxwell's equations tells us that if we pretended that there was some current flowing through our loop S1 or any one-dimensional hole, like for example the z-axis or some sort of like a spiral or something, then that magnetic field would be exactly the function which has 0 curl, but it's not the gradient. Okay, so that still begs the question of how can we compute such a magnetic field? And the nice thing is that there is an explicit formula for how to do that. And that is given by the so-called Biot-Savart law, which says that B is equal to mu naught over 4 pi times the integral over gamma of I dl cross r hat over r squared. Okay, so what are each of these terms? I is going to be our constant current that's flowing through our hole here. Mu naught and 4 pi are just constants which appear in physics. Well, pi is math, but you get the point. dl is going to be the tangent vector to this curve S1. And so here I'm integrating over gamma, so that means I'm integrating over whatever hole we have. So this curve is represented by gamma. And dl is pretty much just going to be gamma prime dt. And r hat is going to be, if we're measuring it at this point, then we're going to look at the distance from our point on our loop or our hole here of gamma, and the distance from that point to the point that we're measuring, and that's going to be this vector r, and r hat is going to be the unit vector in that direction, and then this r is going to be the magnitude of that vector. So mathematically, we can just ignore a bunch of these constants like mu naught over 4 pi and I, and we can sort of write this a bit more explicitly. So in this example, what we'll end up with is if we take the vector field f, which is equal to the integral from 0 to 2 pi of gamma prime cross r hat over r squared dt. And here gamma prime is just this parameterization, and r hat and r are just defined as these vectors from the different points of our parameterization of gamma. Then this vector field f, because it's just proportional to our supposed magnetic field B, is going to satisfy the properties that the curl of f is equal to 0 everywhere it's defined. However, f is not equal to the gradient of any potential function f. So in general, if you have any sort of a one-dimensional hole in your space, then you can use a similar process to just take the integral over appropriate domain of your sort of tangent vector to your parameterization of your one-dimensional hole, cross with this unit vector divided by r squared. And if you integrate that, then you're going to get some vector field f defined at the point xyz, which is over here. And if you do that for all points, then you're going to get some vector field which has zero curl everywhere outside of your hole, and is not going to be the gradient of any function. And sort of to see like the sort of property that f is not defined over your hole, we can look at this integral and see that sort of has a denominator of r squared there. And r is the distance away from this unit circle. So if we were to try to measure, say, the magnetic field somewhere on the unit circle, then what would happen is that this integral would end up diverging. And so the magnetic field would not be defined there, but it's defined everywhere away from the unit circle. Okay, so that essentially gives us a very constructive method of saying if we have R3 minus some curve C, so let's just summarize a bit. We have R3 minus some curve C, and this curve C is given by parameterization gamma. So what I mean by that is you have three-dimensional space, and you're going to be missing some loop C over here, and this is given by gamma of t. Then what you can do is you can take this line integral f, which is given by f is equal to the integral of gamma prime cross r hat over r squared dt. And this vector field f is going to have the property that f is defined on R3 minus C, and it's going to have zero curl everywhere on this domain, but it is not going to be the gradient of any vector f. And so this is kind of cool that sort of electromagnetism has this sort of a relationship between topology and calculus lurking behind it. So now, similarly, I claim that if you were to take the electric field generated by some charges, then that would give you some vector field which has zero divergence, but is not the curl of anything. So to see why that must be true, you can again look at Maxwell's equations. And one of the infinitesimal Maxwell's equations tells you that in places where there's no charge, you're going to have that divergence of E is equal to 0. However, you also have that the double integral over any surface S of E dot dA, where A is the normal outward-facing surface element, is going to be equal to, is it epsilon naught times the enclosed charge. And so what that means is that if you were to take a surface containing the origin, for example, the S2 that we had in the last video, then if you were to take the surface integral of your electric field over that surface, then it would have a non-zero value because there is charge inside. And similarly, if you have a bunch of different charges, then you can construct a vector field by figuring out what your electric field is, and that'll give you a vector field which has zero divergence, but is not the curl of anything because of a similar analysis that we went through last time of analyzing Stokes' theorem in relation with the divergence theorem. Okay, so now there's an interesting curiosity that happens here, which is what if we consider, again, our space R3 minus the unit circle. So here we're going to have S1 in the xy plane again, and we're going to look at R3 minus S1. Now what we can do is, instead of imagining that there's some current flowing through S1, we can imagine that there is instead some charge Q here. And instead of calling it Q, let's call it lambda, I guess, dt. And so what that means is in this little segment of length dt, there's going to be some charge lambda dt. Okay, and what we can do is we can analyze if there's some charge in this unit circle, what's going to be the electric field at some point here. Well, if we compute the electric field at some point, then by these two laws, it's also going to have zero divergence. But if we choose some surface which contains the unit circle, like a big enough unit sphere, then the integral is going to be non-zero if we assume a constant non-zero charge on the unit circle, which means that we're going to have a non-zero vector field which has zero divergence and is not the curl of anything. So one way that you can construct this is, for example, you can do the classic trick of taking a voltage, which is going to be equal to epsilon naught over 4 pi times the integral over your loop of lambda dt over r, I want to say. And then you can take E is equal to the gradient of this potential function v. And then this will give you an explicit formula if you integrate over your loop gamma, which is the parameterization here. This will give you an explicit formula for an electric field which has zero divergence everywhere, but is not the curl of anything. And so that begs the question, like, does this really measure zero-dimensional holes? Because in this case, we have sort of a one-dimensional hole, but we still have something which satisfies this property. So that will sort of be answered in the next question as we explore what these things actually mean, and we'll give a definition of what cohomology actually is in 2 and 3 dimensions.